Hello everybody, welcome to another video lesson. Today we're going to look at sum and difference identities for our trigonometric functions. We're going to be able to find trigonometric values and verify trigonometric identities using our sum and difference identities. So let's hop into what these identities are. Okay, go ahead and pause the video, make sure you get all of these down. And I'm going to go ahead and prove just one of them. We don't have time to prove all of them, but let's go ahead and prove this top one here, this sine of a plus b. We're going to do that with this diagram right here. Okay, so we have angle A and angle B, and really A plus B is going to beat this angle right here, right? So this is what we're trying to find the sine of. And in order to do that, we need, if you can see here, we've got a few triangles within here. So we've got this green one for angle B. Okay, so we've got a right triangle here. Notice our right angle is here at F. And for A, we've got this red triangle here. Notice our right angle here at D. So in order to find out what A plus B is, we have this right triangle here. However, we're going to need this side CG, right? This length CG here, we need to figure that out. Now notice here I have from this kind of origin point to G, that's going to have a length of 1. Okay, so that has a length of just 1. So if that's a length of just 1, let's think of what the sides of this green triangle are. Well, if we have a hypotenuse of 1, then aren't those sides just the sine and cosine values? They are, right? So GF is going to have a value of sine B, and from the origin here to F, that's going to have a length of cosine B, cosine of angle B. Okay. Now, one other thing I want to get out of the way, because we're going to need this angle G right here. Okay, this kind of smaller angle. So let's think about this. If I have a horizontal line here and a horizontal line here at EF, and I have this line cutting through both of them from the origin through F, then what is this angle going to be right here if this angle is A? Well, isn't this angle also going to be A, right? Remembering that from geometry class? Okay, and then if this is A and this whole angle F here is a 90-degree angle, then wouldn't this remainder here be 90 minus A? Because this whole angle is 90 degrees and this little chunk of it is A, so then the rest of it would be 90 minus A, right? And then if I look at this here triangle, this kind of top triangle here, then if E is a 90-degree angle, and this angle here is 90 minus A, well, don't all three of these add up to 180? So if they all add up to 180, and this is 90, and this is 90 minus A, then this angle G right here is going to be A. Okay, so just looking at this little triangle here at the top, finding out that that's A. And we're going to need that here in our proof, okay? Alrighty, so what are we looking for? We're trying to find here the sine of this, now kind of drew it in blue here, angle here, A plus B. And we need that again with GC. Okay, we need this length here because if we take a look at this triangle, right, if this is my right triangle, sine is going to be the opposite side over the hypotenuse. And again, the hypotenuse in this case is going to be 1, right? So if sine of A plus B is the opposite side of GC over my hypotenuse of 1, then the sine is actually just going to be this length of GC. Now we're going to go ahead and break this up into two line segments. So I've got segment GE here, and then I've got this segment EC. Okay, so I've got GE and EC, and I'm also going to kind of rewrite this because EC, since this is a rectangle right here, is the same length as FD, right? So now GC I'm going to rewrite as GE plus DF, okay? So this length plus this length here is going to give me the total length of this whole purple line that I'm looking for. So now let's take a look at our red triangle here, and let's think, trying to find the length FD here. Well, what happens if we write out the sine of our angle A? Well, sine of angle A is going to be the opposite, which is this length DF over this hypotenuse right here. And remember, this hypotenuse, we said, has a length of cosine B, right? So if that is the case, then sine of A is going to be df over cosine B. Now, if I solve that for df, I would just multiply both sides by cosine B, and I would get df is equal to sine of A times cosine of B. Okay? Almost done, I promise. Okay, so now let's take a look at this small triangle up here at the top. Now, I'm going to be interested in finding out what this GE is. And I know here that this is the same as my angle A. So if that's angle A, how could I find out what this side GE is? Well, we're going to do that by writing out the term cosine A. Cosine A is going to be adjacent, which is going to be GE, which is what we're interested in, over the hypotenuse, which we said has a value of sine of B. Okay, and then if we solve for GE, GE is going to be sine B times cosine A. So if I just plug in for GE into here and for DF right into here, I'm going to get that sine of A plus B is equal to sine of A cosine B plus cosine A sine of B, which is what we have up here for our identities. So a little bit of a complex proof there, but that is how we would prove our sum identities, and we have similar proofs for all of our other ones. So we're going to go ahead and move on to some examples. All right, example 1, finding a trig value. We're going to find the exact value of our expression here of sine of 15. Now notice here it says exact value, meaning I'm not going to just go to my calculator and plug in sine of 15 degrees. I'm not going to do that. I need to have the exact value. Now for exact values, we typically look at our unit circle, right? However, we don't have an angle of 15 on our unit circle. That's okay though, because 15, well, what two numbers can I add or subtract from each other to get 15? Especially ones that are on, I'm looking for numbers that are on my unit circle, right? So if I were to subtract 30 from 45, so 45 minus 30, that gives me 15, right? And look, I have an angle for 45 and an angle for 30, so that's great. So I'm going to instead look at the sine of 45 minus 30 in this case. Now, this is our difference identity for sine, so that's going to be sine of 45 times cosine 30 minus cosine 45 times sine of 30. And we can find exact values on our unit circle of all of these terms here. So sine of 45 is going to be root 2 over 2. Cosine 30 is going to be root 3 over 2. And then minus cosine 45, again, root 2 over 2. And sine of 30 is 1/2. So I can multiply these out and I get root 6 over 4 minus root 2 over 4. And to fully simplify, we would say root 6 minus 2 over 4. That would be our exact value there. Okay. So you guys pause the video and do the same thing, but try to find the exact value of cosine of negative 75 degrees. All right, here's our process here. I used 45 minus 120, that equals negative 75. And then we go about the same process, but with cosine, and we get root 6 minus root 2 over 4 again. Okay, looking at our applications here, we have harmonic motion of an object can be described by, we have this trig function right here. Y is equal to 4 cosine of 2 pi t minus pi over 4, where x is the distance from the equilibrium point in inches, and t is the time in minutes. Find the exact distance from the equilibrium point at 45 seconds. Now, if I were to think of this graphically, okay, anything in harmonic motion just means it has it's going about this wave form like we have here. All right, so our points of equilibrium are where our velocities are going to be maximized and our accelerations are minimized. So in the context of this problem, it's just going to be where we are crossing our horizontal axis. Keep in mind my horizontal axis here, I have a t for time for horizontal axis, and then my vertical axis is the distance, okay? That is the distance from our equilibrium point. Okay, so we're looking for the exact value from the equilibrium point, okay, the distance from the equilibrium point at 45 seconds. Now, again, with the exact distance, I'm looking for no decimals. So what I don't want to do is just plug this directly into my calculator and say, oh, that's about negative 2.83 inches. We don't want to do that, okay, because I'm looking for exact distance. However, what we can do is say that A is equal to 2 pi t, where t is 45 seconds, which is going to be 3/4 of a minute, okay, because time is in minutes here. So keep that in mind. And B is going to be pi over 4, right? So really what we're looking at is 4 cosine of A minus B, right? So I'm going to say 4 brackets. So my 4, I'm going to kind of hang out as a coefficient and just figure out what this cosine of A minus B is first. So cosine of a minus b would be cosine of 2 pi times 3 over 4 times cosine of pi over 4 plus sine of 3 pi over 4. That's just simplifying this 2 pi times 3 over 4. That's how I get this 3 pi over 4 here. Just simplify that. Times sine of pi over 4. Now I know that the cosine of 3 pi over 2 is actually 0. So this whole term here is going to go to 0. So that's gone. All right, now the sine of 3 pi over 2, that's actually -1. And sine of pi over 4 is root 2 over 2. So here I have my distance x is equal to 4 times negative root 2 over 2, which can simplify to -2 root 2. So to give a contextual answer here, our distance is it's going to be 2 root 2 inches below the point of equilibrium. So it's going to be, say, somewhere down here, down there, at 45 seconds. Okay, last example slide. Here we're going to do some verifications here. We're going to verify this identity, sine of 90 degrees minus theta is equal to cosine. Okay, so keep in mind what we have here is the difference identity for sine. So this is going to be sine A cosine B minus cosine A sine of B. So that's going to be sine of 90 cosine theta minus cosine 90 sine of theta. Now cosine of 90 degrees is 0, so this whole term cancels out. And sine of 90 degrees is 1, so I'm left with just cosine theta. Cosine theta equals what we have here, cosine theta, so that checks out. All right, you guys pause the video and see if you can verify that cosine of 90 degrees plus theta is equal to negative sine theta. All right, there is your verification there, guys. Those are your steps. And guys, that is it for this video, so good luck with your practice.